നമ്മൾ ഫ്രീ ഇലക്ട്രോൺ ഫെർമി ഗ്യാസിൻ്റെ ആപ്ലിക്കേഷൻസാണ് പറഞ്ഞുകൊണ്ടിരുന്നത്. അതിനകത്ത് ഒരെണ്ണം കൂടെ നമുക്ക് പറയാനുണ്ട്. That is the thermal conductivity and Wiedemann Franz law. This is the fourth and last application that we are explaining using the free electron Fermi gas model. So you know the difference between thermal conductivity and electrical conductivity. Electrical conductivity is the conductivity in metals triggered by an electrical field or electrical force. And in thermal conductivity is the motion of the electrons that is triggered by pressure like heat energy. So this is the difference between thermal conductivity and electrical conductivity. So for a collection of particles with velocity v, heat capacity per unit volume c. So we are considering a collection of particles with velocity v and heat capacity per unit volume. This is heat capacity per unit volume and mean free path L. Their conductivity, thermal conductivity can be represented as K is equal to 1 by 3 C into V into L. I have given the derivation of this equation at the end of this note as appendix. So you have to submit it as an assignment for this class. Assignment derivation of this equation. I have already given the derivation at the end of this note. So you should submit it as an assignment. That means you have to study the derivation. Okay. So the thermal conductivity can be represented as 1 by 3 CVL. Thermal conductivity represented by the letter K. For electron gas, only electrons very near the Fermi level take part in thermal conductivity. Also in electrical conductivity, as we have discussed in our previous classes. So only electrons near to the Fermi level contribute to thermal conductivity. So the velocity of the particle can be represented as velocity of the particle at the Fermi level. So a suffix F will appear here. Now the mean free path L can be represented as velocity into time, Vf into tau. Now this is mean free time between collisions and this is the distance traveled between each collision. This is mean free path. These terms we have already explained in our previous classes. Now the thermal conductivity due to free electron gas is given by thermal conductivity due to free electron gas can be. So what we are doing is we are substituting for V as Vf and L as Vf into tau in this equation. So we will get K thermal conductivity due to electron as K electron, as this is the general expression. K is equal to 1 by 3 CVL. So for electron gas we are representing as suffix EL, KEL as 1 by 3. This is the heat capacity per unit volume. So we have to substitute for electron gas the electron heat capacity per unit volume. So this is CEL by V, and for V we are substituting Vf and L as Vf into tau. So this is Vf square into tau. So this equation will become like this. Now we have already derived the equation, the electron heat capacity CEL as pi square by 2 into n into k T by Tf. For this equation refer the class of heat capacity. We have already derived this there. So now substitute numerator and denominator by k. So in the numerator it will become k square t, denominator ktf. Where ktf is the Fermi energy Ef, which is equal to half m Vf square. So if we substitute this equation here, instead of ktf we are substituting half m Vf square. So this 2 will cancel, pi square n k square t divided by m Vf square. Now the thermal conductivity will become 1 by 3 into 1 by V pi square n k square t m v ef square. So what we are doing is we have got the expression for C electron, that is electronic heat capacity, like this. So we are substituting this term in the equation of thermal conductivity. So we will get thermal conductivity like this. So the final expression will be pi square into n k square t tau by 3m, where we have substituted capital N by V as number density n, small n. Here both electrons in thermal conductivity, both electrons and phonons contribute to thermal conductivity. In pure metals, the electron contribution is dominant at all temperature. So in pure metals, always the electron contribution is the dominant factor. In impure metals, what happens is impurity, some amount of impurity or disorderness may present. So the electron mean free path may be reduced by the collision of these electrons with impurities, and the phonon contribution may be comparable with the electron contribution. So the phonon and electron contribution may become comparable in the case of metals where impurities or imperfections present. Okay, so this is about thermal conductivity. Now what is Wiedemann-Franz law? Wiedemann-Franz law states that for metals at not too low temperature, the ratio of thermal conductivity to the electrical conductivity is proportional to temperature. This is the Wiedemann-Franz law. This happens at not too low temperature. With the value of the constant of proportionality is independent of the particular metal. So this can be equated to a constant. So K by sigma is equal to L into T, where L is equal to K by sigma T is called the Lorentz number. L is called the Lorentz number. This is the proportionality constant here. Now we have already derived the expression for K, thermal conductivity, just above. So this is that expression, and we have derived the electrical conductivity expression as in our electrical conductivity section. So dividing these two, will get pi square by 3 K by E all square into T. So K by sigma is proportional to T. So this term is representing L. So L is pi square by 3 into K by E all square. This is Lorentz number. If you are substituting the values of this constant here, pi is constant, K is constant, Boltzmann constant. So if we are substituting these values here, we will get 2.445 into 10 to the power minus 8 watt ohm per degree. Here we assume that the relaxation times are identical for electrical and thermal processes. Experimental values are in good agreement with this value. At low temperatures, T very much less than 0, L tends to decrease. The value of L tends to decrease at very low temperature. So this is about Wiedemann-Franz law. Now the derivation of this equation, heat capacity, thermal conductivity, K is equal to 1, the final expression is K is equal to 1 by 3 CVL, is given as appendix and at the end of this note. So you have to submit it as assignment. Okay.